Okay, last Wednesday, I don't think anyone could have foreseen that we were going to win in Miami again and then be able to possibly close out last night. Had that been the case, I would have known ahead of time. I wouldn't have made this exam due today. So here's what I'm going to do. If you have the exam ready to go today to turn in, I will accept it, and you'll get bonus for having it done. Anyone who needs more time has till Wednesday. All right? So if you don't feel real good about everything, no penalty. You can turn it in Wednesday. But if you have it today, I'll take it up right now, and you'll get bonus points. Yes. It's today or Wednesday. Anytime after today would be considered Wednesday. So I did say that I will offer bonus for anyone who turns it in early for all the mini exams, who turns them in early, but today's kind of the exception. I'm just taking it as bonus today, if you have it, but it won't be considered early tomorrow. That answers your question. Okay, so if you have it ready, you can hand it to me. Let's see. Couple there. Oh, watch it. Thank you. Stapler. There happens to be one up here on the counter. Can't guarantee that will always be here, but yeah, last night around 1 o'clock in the morning, I was thinking, man, I wish I could have just given everyone the day off today, Is the parade Wednesday? Have they announced that? They did announce it? Wednesday at 6? Okay. We might, yeah, you have to get there real early. Yeah. I don't know, there might be a chance that we actually do cut out early, maybe on Wednesday. Just depends. If it is at 6 on Wednesday. It's at 4:30? Yeah. All right, y'all ready to get started? Got lots to do today. Let me make sure my phone is quiet. Yes. If you just came in, I'll take the exam now for bonus, or you can turn in Wednesday, no penalty, if you want more time. If you change your mind, come get it. Alrighty. Well, I have your other mini exam to pass out to you. Where did I put that? I thought I did. I may have to go grab it from my office in a little bit. I thought I put it in my bag. All right, let's get started with our next topic. We talked a little bit about this last class at the very end, trying to find distances using our knowledge of vectors. And there are basically two formulas that we looked at. One is the formula we use to find the shortest distance between a point and a plane. So if you're given a point, x1, y1, z1, and you're given a plane, the equation of plane, which looks like this, then all you have to do to figure out the distance, shortest distance between that point and that plane, is take the normal vector of the plane, n, dot it with b take that magnitude and then divide it by the magnitude of the normal vector. Now, the vector b in this is the vector that goes from any point on the plane to the point you're looking at, right? So that's your b vector right there. So we're going to do an example here, but I don't think I want to run through the whole geometry of it again because I did that last class. Let's just get to the example. Find the shortest distance between these parallel planes. So how do you think you're going to find the shortest distance between two parallel planes? What's that? The formula I just gave us is the shortest distance between a point and a plane, right? Here I want the shortest distance between two parallel planes. So how can we go about doing that? Well, if they're parallel, though, there is a shortest distance, right? Oh, just the actual distance? The distance, it's basically the distance between the planes, right? Like that distance there. Okay, so you could use the direction. You mean the normal vectors for the planes? What can we say about the normal vectors of these planes if they're parallel planes? The length of the vector will be the shortest distance between the planes. Will it? Well, if it's normal for one plane, it'll be normal for the other. And the orthogonal vector between two parallel planes would be the shortest distance. So if I have a plane, I always have a normal sticking out of it, right? But that normal is not unique. In other words, it could be, twice as long, 3 times as long. It could be pointed in the other direction. And then I have another plane. It happens to have the same, well, it doesn't have to have the exact same normal, but it has to have a normal that's parallel, doesn't it? The normal on both of them have to be parallel if the planes are parallel. But the length of either one of these vectors is not necessarily that distance between them, though. Right? What it, the start point is a point on the first plane, and the end point is a point on the second plane. Then that normal will be normal for both planes, and it will also be the distance between the planes. Not necessarily. Look, back up. What do we need in the geometric construction of this formula? What do we need to find the shortest distance between a point and a plane? We have to have a point on one of the point that we're trying to find the distance from that to a plane, right? But if I give you two planes, right, then how can I use this formula? Just pick a point, any point on this plane, right? Any point on one of the planes, right? Just pick a point that exists on one of those planes. And then find the shortest distance between that point and the other plane. And that should be the same distance, the shortest distance as between the planes. Does that make sense? Let's see, if I have a plane like this, let's say I have another plane down here, right? They're parallel. Then if I pick some arbitrary point on this one, then I should be able to find the shortest distance down to that plane, right? Now, what if I had picked another point over here? I would still have a shortest distance to that plane, correct? And those distances should be the same, shouldn't they? And that distance should be the distance between the planes. So the fact that we were given two planes in the problem, that's trying to complicate it a little bit. Really, you only use one plane to get a point on it, and then you chunk the plane. You don't need that one anymore, and then you work with the other plane. That make sense? Okay, so let me jot down the planes we have. Plane 1 is x plus y plus z equals 5. Plane 2 is 2x plus 2y plus 2z equals 20. Sometimes people will look at this and they'll say, oh, the shortest distance between these two planes must be 5. How do you think they do that? Divide everything on this right here, right, by 2. and that's 10. Agreed? And then they say, oh, look, the only difference between these two equations is there's a 10 here and a 5 here, so the difference must be 5, but that's not correct. All right, so don't do that. That's a mistake. So let's start off by finding a point on one of the planes, all right? Can we do that? So somebody give me a point. You want to work with plane 1? Give me a point on plane 1. Any point that you can think of. 1, 3, is that what I heard? 1, 2, 3. 1, 2, 2. Is that okay? Does that point live on the first plane? Yes. Okay, so I have right now my x1, y1, z1, don't I? Now, in order to use the formula, I also need the normal vector of the other plane, right? What's the normal vector of the other plane? How can you find the normal vector of a plane if you're given the equation? Coefficients of x, y, z, right? So the coefficients are 2, 2, 2. Could I scale that and use 1, 1, 1 instead? Yes. So I have a normal vector. I have a point. How do we find shortest distance? Well, given a point and a plane, we need to compute the vector b. That vector b has to go from any point on, this is plane 2. That's the one we are working on the ground. Here's the point that we grabbed. This was 1, 2, 2. We need to pick any other point that lives on plane 2, right? And then create a vector that goes up to 1, 2, 2. And we'll call that b. So now we need to come up with a point that lives on plane 2, right? Anything we want. So what lives on plane 2? $550? Y'all agree 550? Yes? Okay. So I could pick this point right here to be 550. And now let's create the vector b. The vector b goes from 550 to the point 1, 2, 2. So we do 1 minus 5 is negative 4. 2 minus 5 is negative 3. And then 2 minus 0 is 2. Everyone agree that that's our b vector? Okay? Now the formula, which is in note 10.5.19, is we need to find this distance, which we'll call capital D. It's the magnitude of n dot b over the magnitude of n. So what's n dot b? Just dotting the two vectors, right? 2 times negative 4 gives us negative 8. And then 2 times negative 3 gives us negative 6. 2 times 2 gives us 4. Right? All over the magnitude of n. What's the magnitude of n? Square root of 4 plus 4 plus 4, right? So root 12. And you said the top was what? 10? Right, 10, and then we take the absolute value, so we have 10 over root 12. And you could take out, 2 out of that root and cancel things out or whatever, or just leave it like this, doesn't matter. Or you could get into decimal approximation. Okay? That's the shortest distance between those two planes, parallel planes. Y'all agree that they have to be parallel, or it makes no sense to talk about shortest distance, right? If they're not parallel, they hit each other, so there is no shortest distance. Well, it would be 0, where they hit each other. All right, no questions? Okay, the next idea was finding the shortest distance between a point and a line, right? This is very different, right? A plane versus a line. And the way we did it, again, you can go back and look at the video from last class. I did the construction here. We picked a point Q, picked a point R. So we actually have to have 2 points on that line in order to create this vector A. So all vector A has to be is a vector that lives on the line. And I said last class, we could actually just use which vector instead of creating our own, the direction vector of the line. If we have the equation of the line, the vector equation, we can just use the direction vector as A. And then you do that vector B. So you do have to connect a point, right? And then we use our knowledge of trig. And then I showed you how we took this equation, we introduced magnitude A over magnitude A, because the numerator up here is actually the magnitude of the cross product. So this is our final formula. A here is what? Any vector that lives on our line, so it could be our direction vector, right? And B is a vector that connects any point on our line to the point in question, all right? So some similarities to the plane problem, that we still have to create that vector that connects where we're going to that point. And let's just apply that one now to this example. Find the shortest distance between the point 3, 6, -7 and the line through 2 points. So 3, 6, -7. And then our line goes through 0, 3, 5, and -4, 9, 10. All right, so we have our line here. We have our point up here, right? And our line doesn't have to be flattened out like that. It could be like this. We're trying to find this shortest distance. So it's like we're dropping a perpendicular down to the line. So what about your vector A? How can we get the vector A? Yeah, that's the vector that lives on this line, right? So it could be the one that connects those 2 points. Let's say those 2 points right there, right? Just create that vector. So A in this case would be what? -4, 6, 5. The only thing we have, the only thing left is to create a vector that goes from any point on this line to the point in question, right? So why don't I just create that one right there? And I'll call that our B, right? And this point here was 0, 3, 5. So what is the vector connecting those? B. What is that? 3, -9, -12. You'll agree with that? Any questions on the construction of this at all? Yes. Yeah, if you're going the other direction. What's that? Did I write the point wrong in the problem? Oh, it's +6. Thank you. Gosh, good thing we caught that there. Right here, that's +6. So I did the calculation right. I just wrote it down wrong. Then how does that change this? That's a 3. Sorry about that. Y'all see what happened? I just copied this down wrong. If y'all need more light over there, you can pull the blinds up if it's too dark. Okay. We okay now? Okay, so what do I have to find now? Cross product, right? And the way we did cross products last time is I'm going to write the B right underneath the A like this. And I'm going to do that so I can do that thing that we did in class last time where you kind of, if you wanted to do the I, right, to find the I component, you cover up these two, and then you would do the determinant on this, right? So, and then we would cover up this one, do determinant, and then take the negative, and so on and so forth. Did anybody finish programming that on their calculator? Did anyone try and do the program yet on their calculator? No? Okay. All right, so what is this cross product then? I was hoping someone would just type in their calculator for me. Do we really want to go through it? Okay, we'll go through it. So what's our I component going to be? Whoa. 6 times negative 12, right? So negative 72, take away another 15, right? Negative 87, and then cover up this one, 48, take away 15, right? And then change it. So what is that, negative 33? Positive? Positive, right? And then you take away and then change the sign. So negative 33. What about the last one? Negative 12, take away 18. Negative 30. Do y'all agree with that? I need to start bringing my calculators. If y'all aren't going to do it, I guess I'll bring mine. Now we need a magnitude, right? This is A cross B. We need its magnitude now. So you have to take, this squared plus this squared plus this squared, take the square root. Go ahead and get that. If someone has their calculator, get that and give me a decimal answer, approximation. Let me make sure I didn't throw mine in the bag. Doesn't do any good on my desk. What do you got? 97.8? Any seconds on that? Okay. So that's the magnitude, right? All right, then in the formula we have to divide that by what? Magnitude of A. So I'll do that on top left over here. The magnitude of A is approximately, what's 16 plus 36 plus 25, take square root. 8.76. 7 seconds on that. Yep, okay, then divide this by that, and that's your answer. So the distance will be approximately, what is that, like 10 something? 11.1? Good enough. Do you understand the idea, though? I mean, that's the main thing. Anytime you're trying to find the shortest distance between a point and a line, you'd use this formula. Now, let me give you an example of a problem that would be something like on a take-home, right? I give you a sphere, right? Give you the equation of a sphere. And then I give you a plane. And then I give you some other plane. And those two planes intersect each other. When two planes intersect each other, what do they form? Where they hit each other, it's a line, isn't it? So we have this line of intersection. So what do you think I would ask you here? Well, that's one thing I could ask, right? But a problem like this, what I would say is, what's the shortest distance between the center of that sphere and the intersection of those two planes? Right? The big picture is that you're just trying to find the shortest distance between a point and a line, right? But to get to the point, you have to find the center of the sphere. So you complete the square and do all that stuff, right? Then over here, to get the line, to find the equation of the line, you have to use what we did in class last time. To find the equation, the vector equation of the line of intersection of two planes, what do you have to do? Y'all remember that at all? You have to take cross product of what? The two normals of the planes. That'll give you a direction vector. And then you need a point on the intersection, right? So you have to find a point in x, y, and z that satisfy both plane equations at the same time. So we did that problem by itself once, but this is how I would throw it all into one big problem. Make sense? Okay. All right. That's going to do it for 10.5. We're going to move to 10.6. My 10.6 might look a little different than your 10.6. And does yours still have that typo on 10.6? It says quadratism or something like that, surfaces? Oh, it is? Okay. Good. So cylinders and quadratic surfaces. So let me tell you a little bit about how this section is going to work. We could spend a lot of time in this section, all right? Me sitting up here trying to help you learn how to graph all of these different things by hand, because that's all this section is really about, is these surfaces that we get in three-dimensional space. And before computers, in order to draw a surface, I mean, we really had to have like a good technique to do it. But since we have computers nowadays, I'm just going to kind of push through this section quickly, and you'll be responsible for just being able to associate an equation to its graph. Like we know that if you have something like x squared plus y squared plus z squared equals 9, we should all be able to look at that, recognize that that's a sphere, radius 3, centered where? At the origin, right? Well, there's a bunch of other equations that involve x, y, and z, where there's squares involved, that give you things other than a sphere. And that's what this section is about, how to identify the subtle differences between them and what they give you. So let's move through this. All right, the first is just a reminder in two-dimensional space, x squared plus y squared equals r squared was a circle, right? Center at the origin. But in two-dimensional space, if we then took the equation and slightly modified it, where you divided your x squared by some constant, and you divided your y squared by some constant, and your right-hand side of the equation was a 1, then you would get an ellipse, right? And what if a and b are the same number here? What if a and b are the same? It's circle, right? So a, changing the value of a changes the width of your ellipse, and changing the value of b changes the height, right? Okay, and in two-dimensional space, a hyperbola was the same equation as the ellipse, except for the negative in between, right? Okay. And then, of course, change those like this. Okay, now in three-dimensional space, we're going to want to know what surfaces look like. Remember that the three variables that we have in 3D are x, y, z, right? The way to draw something in three-dimensional space without a calculator is by doing this thing called traces. And you could draw it by hand. And I'm going to try and give you like one basic example of how to use traces to draw something by hand, and you'll quickly agree with me that it's way too much work. Okay? I mean, it is. But we need to know what a trace is, so that's why we have to kind of talk about it. All right, so our first quadratic surface, or our first surface in this section, is a cylinder, right? A cylinder. Cylinder's beer can, right? Just a beer can goes each direction forever. Now, when you have a cylinder, the traces of a cylinder are circles and lines. So let's take a look at a cylinder. Take this out of here. Okay, there's your cylinder, right? Three-dimensional space. And notice that this is the equation. It's kind of far down here. Okay, that's the equation right here. So let's notice what we have here. Our x variable is squared, our y variable is squared, and then we have a constant, right, on the other side. The variable that does not appear here is z. So z is not in the equation. And I want you to notice which way that this cylinder opens, or think about is which axis does the cylinder go down? The z-axis, right? Can we all agree on that? So whichever variable does not appear is the axis which the cylinder goes down. And imagine coming in here and let's take the XY plane, okay? That's the XY plane. And move it up and down. Do you all see that? XY plane? Where it hits the cylinder, right here, creates circles, doesn't it? Creates circles there. And if I move that up and down, everywhere I hit the cylinder, I have a circle. So where the heck is it? Let's see. Yeah, should come in. There we go. You can see that the blue circle right there, right? So that's why they say that a cylinder, all the traces are circles or lines. If I come in with the XY plane and cut it, everywhere I cut it, I'm going to have a circle, right? And then if I come in here with, what plane is that? Those are like XZ planes. They're parallel to the XZ axis. Everywhere I hit the cylinder, I have a line, don't I? Line there, line on the back side, line on the that back side, and a line on the front side. And then if I cut it with planes going the other direction like that, parallel to the YZ plane, then I still have lines, don't I? So what I'm going to try and do now is give you a specific example of a cylinder and show you how you could draw it by hand, acting like we didn't know what this looked like, okay? And then that's the only example I'll ever give you, and that's it, all right? So let's just take one here. How about x squared plus y squared equals 9? Now, what is that in two-dimensional space? Circle, okay, but we're in 3D now, right? In R3, our free variable here is z, so it should be a cylinder, and it should go down the z-axis. Now, let's act like we don't know that. So what I'm going to do is I'm going to start out with some traces. And the first type of traces I'm going to do is I'm going to let z be a number. I'm just going to pick z as something. So let's try this. Let's let z be 0. If I let z be 0, does it have any effect on the equation? No, right? So what happens if I let z be 0? I still get x squared plus y squared equals 9, which we know looks like a circle, right? So what I would do is in three-dimensional space, I would come in here, x, y, z. I would let z be 0, which means I'm on the xy plane, right? I'm flat on the xy plane, and I would draw a circle of radius 3. So it'd be something like if this 1, 2, 3, 1, 2, 3. Draw this circle. Oh, that's terrible. Okay. That would be my circle that lays on the ground. Do y'all kind of see that that circle's laying on the ground? Now, let's try a different trace. Let's let z be 1. If z is 1, does that have any effect on the equation? Well, on the equation, though. Does it have an effect on the equation? No, because there's no z in the equation. So I still want to draw a circle, right? Radius 3. But now my z value is what? 1. So everything needs to be moved up 1. So now I'm going to move up 1 on the z-axis and draw another circle. God, it's just absolutely horrible. Right? Now what if z is 2? Go up again, draw another circle. And you see that if you start putting all these circles together and take all the different z's you could have, you draw a cylinder, don't you? Now that's with me picking z to be constant. Remember, z, when I say z is 0, don't I mean the xy plane? When I say z is 1, don't I mean the xy plane moved up 1? So it's equivalent to cutting my cylinder with planes, right? Now, how would I cut it with a plane that's vertical? Let's say, how do I cut it with a plane that's parallel to the xz plane? That would be y is 0, right? Xz plane would be y is 0. Understand? So I'm going to have new traces now. Now my traces, I'm going to go with y is 0. How does that change the equation? If y is 0. Now it's x squared equals 9, right? That means x is plus or minus 3. Agreed? So think about what this says. Your y-coordinate must be 0, right? Your x-coordinate must be 3 or negative 3. And your z-coordinate is what? Well, I didn't put a restriction on it, did I? So it can be anything you want. So here's what happens. Watch, I'm going to get rid of all these things in here. Okay, if my x-coordinate must be, or I'm sorry, my y-coordinate is 0, then I'm somewhere here, right? But my x has to be 3, 1, 2, 3, and my z-coordinate is free to go and be whatever it wants. So it can go up and it can go down, right? So I draw a line. Now x could also be negative 3. So I go up and I go down. I draw another line. Does that make sense? Now coming back to the picture I had here, what we just did is this. We took, okay, that's what we did right there. Can you all see that? We took the plane, which was the XZ plane. We cut our cylinder, and it drew this line, and then it drew the line in the back, right? Make sense? Then let's say that I do another trace. This time, let's let y be equal to 2. If y is 2, then what do we have? What's our equation become? X squared plus 4 equals 9. So x squared equals 5. So x is equal to plus or minus root 5. Y'all agree with that? So now, again, my y is fixed. I come out 2 on y. My x can be at positive or negative root 5. And then my z is free. So it'll draw 2 more lines. You'll see how that works? So if you put the two ideas together, I think the circles by themselves were enough to tell us it was a cylinder. But the way that traces work is sometimes if you go and you cut it with a bunch of planes this way, XY planes, it's not enough to know what the picture looks like. So then you come in and you try and cut it a different way and see what all those add up to, what those look like. And then you cut it this way, this way, this way, XY plane, XZ plane, ZY planes, and you put all that together and you have a picture. So what we could do is continue going along with this, right? But it kind of becomes tedious to try a bunch of different values. So instead of saying, let's let y be 0 or y be 2, I just say this, let's let y be a constant. What would this turn into? What would our equation turn into if y was a constant? It'd be this, wouldn't it? And that would give me x squared equals 9 minus c squared. And then x must equal plus or minus square root of 9 minus c squared. And since c is a constant, 9 minus c should be a constant, and the square root of constant should be a constant, as long as it's positive. And so this again tells me if I fix y to be a number, then my x will be one of two things, and my z will be free. So that's truly what traces become later, is that instead of plugging in specific values, you just plug in a general constant, and you look at what the result is and see what that is geometrically. Y'all kind of follow that? Okay, so that's our first example. Now, what happens if we just did that? What happens if we change the equation? Now it's x squared plus z squared equals a constant. Well, x squared plus z squared equals constant will be a cylinder, but the free variable here is y. That means it's going to go down the y-axis instead of the x-axis. Or, sorry, instead of the z-axis. So whatever your free variable is the direction it goes. Then if I rewrite it again, two of my variables are squared, right? Addition between them, constant on the other side, x is free, cylinder down the x-axis. All right, the next type of surface is what's called a parabolic cylinder. And I know you have the pictures in front of you, but let's look at what the traces are. If you cut it one way, you get parabolas, and if you cut it the other way, you get lines. So this is it right here. Okay? Now look at the equation. Z equals a constant times x squared. Notice you have only two variables in the equation, right? One of the variables is squared, the other one is not. And one of the variables, of course, is free. Notice the axis it goes down, right? It's like a folded piece of paper, kind of, right? It goes down the y-axis. It goes down the axis of the free variable, doesn't it? If I cut it one way, right? If I cut it that way, oops, I get parabolas, don't I? But if I cut it this way, I get lines. Make sense? All right, so we won't do this one by hand. Now, go ahead.
Oh, I was going to say, so you would find the point at which the plane only gave you one line, and that would give you the trough of the parabola if you were drawing it by hand?
If you were at the very bottom, which in this particular example, to be at the very bottom of this parabola, the trace you would be doing is z equals 0. If z is 0 here, right, then that means x is 0. And your y is free. So if this line right here, x0, z0, right, y can be anything, draws this line. That make sense?
All right. I'm just trying to figure out how to do it by hand. I mean, so I guess you would go down to the 0 point, and then you could take another point and then write an equation for the parabola, because you would have 2 points then, right? And then you could get it back.
What if z was 1 here, okay? But let's just see, and let's just act like c is not even here. What if z was 1? Then you get x squared equals plus or minus 1, right? Or x squared equals 1, which means x is positive 1 or negative 1. So we said z is 1. So move up 1, right? Move up 1. Let's just say that that's 1 right there. Then notice what happens is that any point on that blue line, the z is 1, right? The x-coordinate, looking from the top, the x-coordinate is either out 1 or negative 1. And then the y variable is free, so it draws the whole line. And on this side, the x is 1, the y is free, and the z was 1. Does that help?
Yeah, no, I'm just trying to go over how, if I had nothing but a stick and dirt, how I would draw it. I think I got it.
If you want to do these by hand, I'm more than happy to sit down and go through these. I would say come by my office and we can do some of these, because it's very time consuming to do these. Because if you look at your notes, how many of these surfaces are there? I mean, there's a bunch. And so if I gave you examples, that's all today would be. So I'm more than happy to do that. What I want you to be able to do in this class, though, is this. I give you an equation, and you need to know which type of surface that is. That's our main goal. All right, so here are the other two variations. This one went down the y-axis, right? Y was free. Here, variable not squared, variable squared. The missing variable is x, so it goes down the x-axis. Look at this. X isn't squared, y is squared, z is free, so that paraboloid goes up the z-axis. That number in front, C right there, that changes which way that goes. You can flip it around the other way like that. So that constant will control that paraboloid. All these different variations. All right, the next surface in 3D, ellipsoid. It's an egg, okay? That's all it is an egg. So, I didn't say, it says on your thing, all traces are ellipses. An ellipsoid is a surface where every trace you do is an ellipse. So if you look at this right here, take the XY plane, start cutting it, You see everywhere it cuts it, those red lines, you see those are all ellipses? Now, maybe I can help this make sense by doing this. Let me move this to 0. If z is 0, right here in this equation, if z is 0, right, that forces you down to the xy plane. And what type of equation would be left if z was 0 right here? What's x squared over a squared plus y squared over b squared equals 1? An ellipse. So you would have a specific ellipse there. Now, if z is 1, right, if z is 1 here, yes, z is 1, then this whole thing would be a constant, right? And you could move it to the other side, and then you could divide through by that constant, and these two things would become different. But all it would do is create an ellipse, but it would be a different ellipse. And so you're either shrinking it or making it larger. In this case, the further up z went, the smaller the ellipse gets. Now if we cut it the other way with an xy plane, or no, that's yz plane. I need to switch these. Then notice here, as we cut through, they're ellipses, but the other way. Okay? And the last direction that we would do would be this direction with an xz plane, and again, we have ellipses. Okay, an elliptic paraboloid. So an elliptic paraboloid is a surface where where traces are both ellipses and parabolas mixed together. So without knowing what it looks like, I mean, if you try and think of cut it one way, I've got what? Ellipses, but then if I cut it the other way, I've got parabolas. Would that be the object that would have come to mind? Do you agree this way I've got parabolas, right? If I cut it this way, I've got ellipses. So it's like a big bowl, right? We didn't talk about the variables here. Very, very close to, this is very close to what we had just a second ago. Actually, I didn't even talk about the equation here. Look at the equation here for this one. What do we have for this equation? For an ellipse. All variables squared, right? All variables divided by constants equals 1. That's what an ellipsoid looks like. So this, you have all variables squared, right? But it's not a sphere, it's an ellipsoid. What if all these numbers were the same? What if A, B, and C were all the same? Then you'd have a sphere. Okay. For an elliptic paraboloid, you have a squared, or x squared over a squared plus y squared over b squared, but then your z variable is not squared, and z is over a constant. In that case, you get this. What if you switch it around, same exact format, except your y is the one that's not squared? Well, then look at which way it opens. You turn in your parabola on the side, or elliptic paraboloid on the side. And then you could go the other direction, right? Come out this way. Next one is a hyperbolic paraboloid. So your traces are hyperbolas and parabolas. Okay, so check this out. If I slice it with planes this way, okay, so like XY planes, if I cut it like that, let's take a look up here. We have, looking from the top, hyperbolas, don't we? But if I slice it this way, I'm kind of pushing the limits of Mathematica right now. There we go. Can you all see that those are parabolas? They kind of go off the graph, but it goes up, comes back down. So we have parabolas from the other direction. Now, what's the equation look like here? What's the difference between this and what we just had before this? Subtraction between the two, right? Okay, this one was a hyperbolic paraboloid. So we have, oh no, that's the same one, right? I just switched up what variable was the one that wasn't being squared. So we just start opening it in different directions again. Okay, a cone. Traces are ellipses and hyperbolas are lines. So there's a cone. If I cut it with the XY plane, I get ellipses. If I cut it with the YZ plane, I get hyperbolas. I'm going to bring this out just a little bit. I know it's kind of hard to see this, but can y'all see the hyperbola here, where it hits up here and then down here? If you were to look at it kind of from the top, it's hyperbola. They open away from each other like that. What about this equation? All variables squared, right? However, one of the variables is on the other side of the equation. If you brought that variable back over there to the left, wouldn't it have a minus in front of it? If it had a plus in front of it, right? If they were all on one side and it had a plus, that would not be this, right? Okay. All right, cone. These are just opening it the other directions. We're almost done. A hyperboloid of one sheet. Traces are ellipses and hyperbolas. Kind of looks like a nuclear power plant thing, right? Cooling tower, yeah. Okay, so cut it one way, we should get ellipses. Cut it another way, and we should get hyperbolas, like this. And then finally, well, these go the other direction. Notice the equation here, right? That has a minus there instead of a plus. What would that be if it's a plus? If that was a plus, it'd be an ellipsoid. Okay, so that's why I'm saying you're going to have to be able to know the difference when you look at the equation. Can you just be able to say, oh, that's an ellipsoid, or that's a hyperboloid, one sheet, or the hyperboloid of two sheets. So here's what a hyperboloid of two sheets looks like. So it's kind of like that one we just had, but we brought the center in so much it pinched it off into two, like paraboloids almost. Look at the equation here, and that's what we get. Okay, so let's get to a problem. I think this is a good one to do. So I give you an equation. We want to reduce it in a standard form and then classify the surface. So how would you go about doing this? What's your instinct here? I mean, complete the squares on everything, right? I mean, what we have here is some type of surface, right? It looks like we have all three variables squared. It's just a matter of figuring out which of all these surfaces this falls into. So let's do some completing the squares. The first time I've demonstrated this. Let's see, we have minus y squared plus 2y, and then plus z squared plus 4z, and then we have plus 2, which I'll just move it to the other side, negative 2. So all we do to complete the square is group all of our x terms and y terms and z terms together, right? And then on your x terms, I take half of the coefficient in front of x and square it, right? So what do we get there? We have a 1, right? We're going to take half of negative 2 and then square it. We get 1. What do we do with that 1? The reason I'm bringing this up is I want to know how many of you learned it a certain way. How many of you learned you go take x squared minus 2x, you add 1 and subtract 1 right there? Okay, how many of you learned you add 1 to both sides of the equation? Okay, my suggestion is this way. And the reason why, and you may have run into this in Cal 2, if you ever had like an integral where you had like a square root, and then down here you had something like x squared minus 4x or something like that, and what you wanted to do was complete the square here, right? Then you would take like half of negative 4, and then you'd square, you get 4, right? And then what you would have to do is add and subtract 4 in here. See, there's no equation. You can't do it to both sides in a problem like this. So whenever I complete the square, I never work with both sides of the equation because I'm not guaranteed I'm always going to have an equation. So that's just my personal preference right there. Okay, now, what about here? What do you have to do on this? You have to be careful, right? What do I have to be careful on that? Because I have the negative in front of the y squared, right? So I first have to pull the negative out of the y squared and rewrite that as y squared minus 2y, right? So I'm just pulling a negative out of the y terms. And then I complete the square right here on this, right? So I take half of negative 2 is negative 1, I square it, so I'm going to get a 1, and then I add and subtract it, and I'm going to put it right here. I keep the negative, y squared minus 2y plus 1 minus 1. And then for my last completing of the square, we get what, z squared plus 4z, and then I'm going to do what to that? Yeah, divide by 2, so I get 2, square it, 4, add and subtract 4, and then equals negative 2. Now, because I complete the square, I'm guaranteed those 3 will factor. In fact, it will break down into perfect square trinomial, right? So those 3 things will factor. I should get my x minus 1 squared there. I'll still have the minus 1. Then I have minus, let's see here, y minus 1 squared, and then I still have the minus 1 there. Then this will be my z plus 2 squared, and then I still have minus 4 there. All right, let's put everything together here. X minus 1 squared. How about this? Minus y minus 1 squared. This negative 1, and then this negative 1 becomes plus 1, right? So those are going to go away. And then I've got, the only thing left over there is that negative 4. Take it to the other side, and that's a 2. Okay. Okay. So which of our formulas, if any, do we have all variables squared? Now, do we realize that the minus 1 in here and the minus 1 in here and the plus 2 in here, all that does is it's a shifting of whatever it is. Like if it was an ellipsoid, all that did was move the center of that around, just like the center of the sphere. We just want to know which of those surfaces has squareds on all variables, and one of them has a negative sign, the other 2 have positive, and then we do need to address that 2 on the other side also. So any ideas? I don't know, you should have that all in front of you. So I've got 1 vote for the hyperboloid 1 sheet. What do y'all think? Hyperboloid 1 sheet? Hyperboloid 1 sheet looks like this. This is the formula for hyperboloid 1 sheet. Well, there's several of them, depending on which way you want it to open. Which one of them has, yeah, that very first one. It was x squared over a squared plus z squared over b squared minus y squared over c squared equals 1, right? That's a hyperboloid 1 sheet. That goes down the y-axis, so it looks like kind of like that, right? Down the y-axis. Is that equation like this? Similar. I need a 1 on the right-hand side, don't I? So couldn't I just divide everything by 2? Right? Are we sure about this? Yes? Now, if you did it this way, would all of your A, B, and C, this would be A squared, wouldn't it? And then B squared and C squared? Right? The other side's 1. So technically your A, B, and C are all the same? Is that all right? Are there any other equations that you have in here with all these surfaces that have all your variables squared, all variables squared, with a minus on one of them? We just got to make sure we're not overlooking something. Mm-hmm. Yes. Yes. Oh, yeah, this would be our C. Sorry, that would be our C in the formula. And that would be B. Yeah, just move that whole thing over here. So we're okay? We agree with this? So this would be a hyperboloid, 1 sheet. And we can tell which way it opens by this thing. What's the center of it? What's our center? 1, 1, negative 2. 1, 1, negative 2. So that's all I'm asking for, is come up with the equation, classify it, identify it, find its center, we're done. Did I say 1, 1? No. It would be what's in here. Yep. Nope. This doesn't. This is like our HKL. HKL. All right. That is it for that section. All right. Your homework off of this section, I'm going to give you your homework for that today. It's page 579. It's 21 through 27 odd. So that's just a few problems of doing basically what I just did. Complete some square. You know, I think in your book there is a page where they have a summary of all the surfaces on one page. So if you want to go back, you can take a look at it. Let's see here. It's on page 578. Because what I gave you in the notes is kind of overwhelming, because I would do going down different axes, and I'd go down all three, and that just triples the number of formulas you have. Here they just keep it pretty simple. They keep it down to 1, 2, 3, 4, 5, 6 things here. All right. Any questions on this? Mm-hmm. I did. I apologize about that. Someone sent me a text or emailed me or something, said, hey, where's the 10.4, 10.5 homework? I was like, I got to go do that. I forgot about it. And then I forgot again, got distracted. And I got another email yesterday or text, and so I posted it yesterday. And I think I put on there just, focus on the test, and Spurs play tonight, and we'll see how things go or something like that. Yeah. All right, moving along. So we want 10.7 now. All right, vector functions and space curves. So up to this point, we have talked about vector functions, specifically the vector function of a line, right? We've come up with the vector equation of a line. And it looks like what? What was the vector equation of a line? TV, something like that. That's the vector equation of a line. Now we're going to get more general because, as you might imagine, lines are nice, but not everything that we want to study is linear. So imagine just, you fire a rocket off into the air and it has a path and, starts to go out of control and then eventually comes back to the ground, right? That path is nonlinear, but you'd like to be able to represent that path somehow. So we have the general idea of a vector function. A vector function, R of t, same notation, can be 2 or 3 dimensional. The thing is, your x component of your vector and your y component of your vector are just functions of t. So it's like the clock starts and then where you are, the vector that points to where you are, the x and y components of that vector, or possibly the z component if you're in 3D, are all dictated by some function of time. And those functions can be different for each component. So you can have whatever's happening to your x can be completely different than what's happening to your y. And then over here, also your z. So t is a real number. F, g, and h are just what we call real valued functions, just a traditional function. And this is called a vector function or a vector valued function. So it takes on t, right? It's a function that takes in a time, a t, a number, and it spits out a vector, either in 2-dimensional space or in 3-dimensional space. Some notation, you may have never seen anything like this before, and we may not study it too much more, but a lot of times, people who do more math, this is some notation you might see. When we were talking back in most of our days with functions, we'd take a function like f of x equals x squared. What happens with a function like this is called a real valued function. You take a real number in, right? In, and it spits out a number, doesn't it? Number in, number out. Another way of writing that mathematically is to write, if I write that, then I'm defining f to be a function that goes from r into r, number in, number out. What we're doing right now is we are defining a vector function called r, and what it does is it takes in a number, right, t, and what it spits out is a vector, right, a 2-dimensional vector, or possibly a 3-dimensional vector. And could you spit out a 4-dimensional vector? Sure. Now, we're only going to work with 2 and 3 in here. But what I want you to see is that a vector function takes in, right now, a number, spits out a vector. Single number in, single vector out. All right, so the domain then is real numbers. The range is either a vector in R2 or in R3. So given a vector function in 2 or 3-dimensional space, the f, g, and h functions are called the component functions. Component because with vectors we talk about components, not coordinates. The graph of the function in 2 or 3-dimensional space is going to be a curve. Now, it could be a line, but we do sometimes consider lines to be curves. So we are going to just understand that a line in this case is considered a curve. But the important thing is it is not a surface. Okay, it doesn't draw a surface. It draws a curve. Now in chapter 13, we're actually going to have a new vector function that's going to take on, instead of taking in a single number, it's going to take 2 numbers into it, and it's going to spit out vectors. And that's going to draw us, we'll be able to draw surfaces that way. All right, so for right now, we just have to kind of stick with the curve, and we get to surfaces whenever we're trying to find flux. You heard that before, flux and things like that, physics. That'll require us being able to draw surfaces with vectors. Okay, so here's an example. So here's my vector function. It takes on, these are my two, what do we call these? The component functions, right? These are my component functions. So as I let t go, and I'm going to start t at 0, then, you know, of course, when t is 0, where am I? If t is 0, I'm at a vector what? 0, 1, which is that red vector right there, correct? And then as I let t start to go, it starts to draw these vectors, right? So what I want you to understand here is that the red vectors are what the function is drawing, right? It's just drawing a bunch of those vectors. But the vectors trace out a curve. And so we refer to that blue part as the actual curve of the vector function. Does that make sense? All right, so as time's going on, it's drawing these vectors. For every point in time, there is a corresponding vector. Now let's take a look at this graph. So before I even draw it, forget that we have a third component function here. Cosine t sine t. That's something from pre-cal and cal 1 and some of cal 2 that you hopefully are familiar with. If I just have cosine t sine t in two-dimensional space and start letting t change, what does that draw? Circle. In this particular case, the unit circle, because there's a 1 in front of the cosine and sine, right? That should just draw the unit circle. So what this vector function is doing is it's trying to draw the unit circle. But look at the z-coordinate, t over 5. T over 5 means as you're trying to draw the circle on the xy plane, right? Xy plane is the ground. As I'm trying to draw it, as I go around, what's happening to the z? It's coming up. So instead of drawing a circle, so I'm letting time go now. So as I'm drawing the circle, I'm actually increasing my z-coordinate, so I'm drawing a spring, basically, right? Okay. Or a coil, some sort of coil. But it has a fixed radius. Do you all see that? Fixed radius. All right, so limits. Remember in Cal 1, one of the first things that you ever did in Cal 1 is you studied limits, right? And you discussed the idea that if you have a function, then you can take the limit as you approach some value and figure out what's happening to the function, right? Or you could let x go to infinity and figure out what happens. Well, same thing with vector valued functions. If I want to know what happens as t, right, goes to 0 or t goes to 2 or t goes to infinity, then all we have to do is pass the limit into the component functions. So the limit of a vector valued function is just the limit of its component functions. And that works in 2- and 3-dimensional space. So look at this one right here. And we're going to work this one out. 10.7. Okay, if we're given the vector valued function r of t equals cosine t, sine t over t, and e to the t minus t over t, and I think, well, I'll do this one. I'll just stick with this. What is the limit as t goes to 0 of r of t? That's what we're being asked to find. So according to what I just said, I just have to take the limit of each of the component functions, right? So it's 3 different limits I have to look at. First, what's the limit as t goes to 0 of the first component function, which is cosine t? And that's just 1, isn't it? And that you could get just graphically, right? Or you could get it mechanically, right? T goes to 0, what's cosine of 0? 1. So that's kind of a no-brainer type limit. The next one, a little more involved. Okay, what happens as t goes to 0 here? You get 0 on top, right? 0 on the bottom. 0 over 0 is 1. 0 over 0 is undefined, indeterminate form, right? 0 over 0, when you take a limit, if you get 0 over 0 or infinity over infinity, or some variation of negative infinity over infinity, something like that, that's an indeterminate form. So how do you handle an indeterminate form? Okay, L'Hopital's rule, show of hands. L'Hopital's rule. Okay, if you don't have any idea what I'm talking about, L'Hopital's rule, the hospital. Okay, you do need to, that's messed up. There we go. Anyway, if you have no idea who that guy was and what his rule is, you need to review that or you're going to suffer mightily on the take-home exam. Because there's a problem on the take-home exam that requires a pretty good knowledge of how to apply that rule to not only 0 over 0 and infinity over infinity, but things like infinity to the 0. Things where you had, remember there's a bunch of different indeterminate forms. And some of them are pretty straightforward, like this one, right? How do we deal with the 0 over 0 using L'Hopital's rule? That's right. You just take derivative of top and bottom separately, right? People do it different ways. I've seen people draw an L and circle it. I've seen people draw an H and circle it. Different notation, but this lets everyone know that you have applied L'Hopital's rule. You take derivative of top, which is cosine t. You take derivative of bottom, which is just 1. And now you reapply the limit, and that answer is just 1, right? Cosine of 0 is 1. So please do review if you haven't seen this. Now, how about the last one? Limit t goes to 0, e to the t minus 1 over t. So where does the top go here? E to the 0 is 1, right? 1 minus 1, 0. And on the bottom, 0, so you get 0 over 0, indeterminate form. Apply L'Hopital again. What's the derivative of the top? E to the t. Derivative of bottom, 1. Now let t go to 0 again. You get 1. E to the 0 is 1. So what is the limit then of this whole thing? So we had 3 different pieces, right? So our answer here, okay, here's my answer. My answer is a vector. Okay, the answer is a vector. It's the vector 1, 1, 1. Because what we're saying is this is a vector function, right? It's drawing a bunch of vectors. As time gets closer to 0, what vector is it getting closer to drawing? It's getting closer to drawing the 1, 1, 1 vector. Now, does it actually exist? I mean, look at what is r of 0? It's undefined, right? R of 0 is undefined. But as you approach r, the vector is getting closer to 1, 1, 1. Just like we had in Cal 1. You can have a function approaching something and at that point not be defined. All right, continuity. So after in Cal 1 you talked about limits, then you did continuity. Well, with vector functions, we will say the vector function is continuous at a point A if the limit exists, right? The left side of the limit, the left and right limits exist, and it's equal to the function's value there. So to be continuous, not only do you have to be going to the same place, but you actually have to be defined at that point, just like in Cal 1. All right, describe the curve given by this vector function. Anybody want to throw a stab at that? What does that draw? What's that? Yes. And when you put them all together, It draws. Now, do you see why it's a line? Look, remember how we took this one vector and it had t in front of numbers, and then this was just some other vector. We put them together, and all you had was a combination of numbers and t's, right? And it was t's, linear t's. So this is just like, I can tell you right now that R naught would be what here? 1, 2, 0, right? And the direction vector of this line is -1, 4, -6, right? So by looking at this, we should know that that's a line. The reason I put that up there is just so we don't lose sight of the fact that we've already looked at a specific type of vector function. So when we see them now, we don't want to be like, you know, and lose the fact that it's kind of easy to identify them. Okay, find the vector function for the line segment. Segment. This is the first time I've done one of these. The line segment from a point to a point. We know how to draw the entire line, don't we? Like if someone wants us to draw the line between, you know, that connects 2 points, we can draw the whole thing, can't we? But how do I get you to just draw the line segment connecting 2 points? So let me work this out. And I'm going to do it kind of with a drawing as I go here. I have a point 359, and I have another point -573. So here's one point. That'll be my 359, and the other one is over here. And what I want to do is I want to create a vector function, an R of t, which will draw me the line segment between the two. So just the stuff between them. So I don't want to go past those points. So here's what I can do. I can create my direction vector. Remember how we did direction vector like this? It was the vector connecting the two. So let's create V. What would V be here for us? The way I drew it, it would be -8, 2, -12, okay? And then the point, my R naught, matters this time, okay? Because what I want to do is go from the 359 to the other point. So my R naught needs to be where I started my vector. And that was 359. And now I'm just going to rewrite this using this right here. So R of t would be, if I put it all together, I should have 3 minus 8t, 5 plus 2t, and then 9 minus 12t. Does everyone agree with that? Putting these two pieces together into my my line vector equation. Now, how am I going to get it to work out so it just draws the line segment? Well, look, what if t is 0? What if t is 0 right now? What do we get? We get 3, 5, 9, don't we? So we would be here. What if t is 1? What would you get? -5, 7, -3, which is what? The other point, right? So if t is 0, I'm down here. If t is 1, I'm up here. So if t is anything between those two, 0 and 1, then I should be somewhere on that line segment, shouldn't I? Think about it. By using this direction vector right here, we said that one of those direction vectors takes you the whole way, doesn't it? So if I did half of that, it would take you halfway. So all I need to do to draw the segment is just restrict my t between 0 and 1. If I do that, then I have defined a vector function that draws the line segment. So there's some subtleties I'll just reiterate to you. If you want to draw the line segment between two lines, then what you need to do is create your direction vector that goes from one point to the other, but then your R naught needs to be that initial point of your vector. If you do it that way and put them together and always go from 0 to 1, you'll always draw that line segment. If you accidentally grab the other vector, the other point, right? -5, 7, -3, and you put that here with this, you will actually draw something that's over there if you vary from 0 to 1. Understand? All right. All right, find the vector function and its domain representing the intersection of these cylinders. So this is where things can kind of get a little bit weird. It's like, what? Did we skip something? Like, why are we doing a problem like this already? So here are two cylinders. Notice they do not have the same radius, right? Okay. And if you look at their intersection, I'm talking about that blue curve. You see that blue curve? That blue curve is a three-dimensional curve. And if I take the cylinders out of here, I have two three-dimensional curves, right? What's the vector function? Not this right here, but what's the vector function R of t that would draw that curve? That's what we want. It seems a little troublesome, doesn't it? Like that might be a little hard to do. But physically, geometrically, you understand what we're trying to find? And then in the next section, we're actually going to be able to find arc lengths. So you could actually measure the length of that. So maybe if you're making 1 million of these pipes that come together like that, and you have to weld those, then you know how much welding material you need because you know the length of that arc. I mean, there's so many different applications to this. But the idea is that we take something three-dimensional, we represent it with the function. Once we have it in that form, we can do all the math on it, right? So here's how we would do this one. All right. Do you agree that the blue part being an intersection of two surfaces means every x, y, and z, right? Every point on the blue curves have to satisfy both of those equations simultaneously. Yes? So if I pick an x and a y that works in this one, then that y that I picked here also has to work here. Yes? So let's just start with trying to kind of take a shot at this, all right? Yeah, we're going to have some domain restrictions here, definitely. So, all right, here I go. Starting off with one of the cylinders, and I'm just going to take this one. I could have started with the other one, all right? What I know from this is that, let me write the other one up here just so I can have it. X squared must equal 9 minus y squared, right? Do you all agree with that? Would that help me at all? Look at the other equation. What variables do I have in here? Y and z? If I solve this one for y, then I could set it equal to this one, right? Okay, let's back up just a second though, all right? Before we start solving for variables, could you draw this for me? Okay, that's the cylinder, right? The thing is though, we need to draw it by using a vector function. We need to be able to draw it by starting a clock. Like T starts, let's draw, right? Yeah, is that a question? Comment?
So what if you drew the circle for the first equation, and you drew the circle for the second equation, and you found the line on which the circles intersect? Would that be equal to your domain for y?
The circle for one, the circle for the other. Geometrically?
They should intersect, right?
Well, yeah. Well, they intersect everywhere there, right? Let me bring these in. The question would be, you know, see, if I'm up here, they intersect at that point, right? But if I'm down here, notice that that point's kind of moved back a little bit. So bear with me here. Bear with me. Let me first try and draw a cylinder using a vector equation. Let me start with that. Can I just draw that cylinder on the left with a vector equation? So let me do it. Remember the spiral we had a second ago? That spiral looked like this. It was cosine t, right? Sine t, right? Is that going to work for us? Is that going to draw that one? Well, what's the radius of this one? The radius of that circle is 3, right? This wouldn't work. This draws me the unit circle. So what do I need to modify this with? I need to modify this with the 3 in front. Okay. Right now, do you agree that that would draw me a circle? I just need to determine what's going to happen with the z, right? Do you agree with that? Now, if I want to draw the whole cylinder, I just need to let z be free, don't I? And just let z change and be whatever. But if I want to also live on this cylinder, I have to satisfy that equation, which means that z must be equal to, z squared must be equal to 4 minus y squared, which means z must equal plus or minus square root 4 minus y squared. But what is y? What have I decided my y coordinate is here? When I draw a circle, isn't this the x and this is the y right here? So in order for me to get their intersection, this will draw me the outside of that cylinder, which in my picture, notice that that blue curve, it does lie on the bigger cylinder, doesn't it? That orange one? That blue curve is always on that cylinder. Yes? It's just the fact that the other cylinder is going to force me to be on a certain part of it. So I need to use the equation of this cylinder to be able to move back and forth on that, if that makes sense. So this restriction right here, if I'm saying y is equal to, what did we say y was equal to? 3 sine t. Then if I put that in there and square it, I get 9 sine squared t, right? This is what my z has to be in order to be on the intersection. So I plug that in right here. Now there's actually 2 of them. Right? From our picture, we had 2 different blue curves. Right? So we actually are going to have 2 different vector functions. I'll call this one R1. The other one will be R2. It'll be the exact same thing, but with the negative. Minus 4 minus 9 sine squared t. So going back and thinking through this again, what we did is we said, can we draw this surface? Well, yes, I can, right? But the z was kind of free because that would draw the whole cylinder. Then we used the other equation to solve for z, and then whatever we replaced x and y by, we plugged that in over here. Now, we didn't have x, but we had a y, so we plugged that in, and that gave us our restriction for our z. Now, our x, y, and z all depend on t, and if you were to graph these using a computer, that's exactly what I told this computer to do. Where is it? Right there. Right? I just had it graph that right there. And I had to graph the other one. See, this one right here doesn't have a negative in front. This one does. So I had to graph them both. And then pull out this. Here I'm going to actually show the vectors. And then I think what I'll do is I'll start the clock. So that's drawing that one. And the other one, but my clocks are off, but if I started them both at the same time, it would draw them both, okay? Now, we're not done with the question, right? Damn it. We're about to take a break. I know y'all are ready for one. We have to find the domain, don't we? Or at least I asked for the domain.
I tried graphing the two circles when I got -2 to 2 for the domain of the lot.
-2 to 2. Man, we still have a lot to do in here. Oh, there we go. All right. Well, let's look at our vector functions. Where are they defined, or where are they not defined? So the only problem we have here is a square root, right? We have to be careful not to get a negative under there. So when I talk about domain, all I'm going to look at is this. I need to make sure that I have some control over this part of it. And specifically, I want to make sure that this under here, right, is always greater than or equal to 0. So when is 4 minus 9 sine squared t greater than or equal to 0? Well, that's the same as when, now just do some algebraic manipulation here. This is when sine squared t is less than or equal to 4/9, right? Now we have to be extremely careful when it comes to inequalities versus equations, right? Inequalities, because remember, like if you multiply or divide an inequality by a negative number, it flips it over and stuff. So the standard way to attack an inequality like this is to first just treat it as an equation, all right? Treat this as an equation first. So if I take the square root on both sides, I get sine t is plus or minus 2/3, right? Sine of t is plus or minus 2/3. And now this becomes a pre-cal problem. What is arc sine of sine t? So you do arc sine on both sides. And we have to do both positive and negative. So who wants to take arc sine of, do positive 2/3 first, and make sure you're in degree mode. So our answer will be in degrees. Arc sine of 2/3. What do we have? 41.8? 41.8 degrees. Now do arc sine of negative 2/3. Negative 41.8. Now, we have to be extremely careful here, all right? Because this is saying right here that sine of t can be positive or negative 2/3, right? Think about a unit circle here. Sine is the y-coordinate, isn't it? Sine's the y-coordinate on a unit circle. So if I said, hey, look, sine of some angle is 1/2. We would be right here, wouldn't we? That angle, 30 degrees. But that's not the only place that sine is 1/2, right? Sine could be half over here. What if I said sine of some angle is negative 1/2? You could be down here, right? Or you could be over here. So what our calculator has thrown at us is it's given us these two angles, right? It's given us the 41 and the negative 41. Why doesn't your calculator go on that side and get us answers? Because arc sine is restricted. The domain of arc sine is a restricted domain. So that's why our calculator doesn't give us those answers, but they're there, and we have to know that. We have to know that before we proceed. So there are two other solutions that we need. And they are what? So just add 90, or no, wait, add 180 to get to this one, and then on this one add 180. So your other two should be yeah, the other ones should be 138.9 and 221.8. Okay, those should be all 4. Now, y'all okay with that? I'm not. I added 180. Oh, I'm sorry. I'm going off of what my screen says here, right here, which I think there's some rounding errors in here. I apologize. What should these be? 138.2 and 0.2. Is that right? Yeah. Y'all agree with that? No, I'm adding 180 to this. Add 180. No, that was this one. Look, when it comes to arithmetic, my brain just shuts completely down. So, are we happy with that or not? Okay. You understand we're just adding 180, all right? So, this is when, look, go back up here. This is when I said we have to switch inequalities over because we have to be careful about flipping the sign, all that. So we went and we switched it to an equation. We got 4 solutions. Now what we need to see is if, it's kind of like we broke up our angle into 4 different regions, right? And we have to figure out where this thing works, this right here. So somebody give me an angle that you know real well between here and here. How about 0? Okay, so plug 0 in here. What's sine of 0? 0, is that less than 4/9? Yes, so that region works. Okay, someone give me an angle up in here. 90. What's sine of 90? 1. 1 squared. Okay, is that less than 4/9? No, that region does not work. Then you try something over here like 180. Sine of 180? 0. It works, right? And then you'd use the last one over here, and it wouldn't work. So our angle, our answers are between here and here. So between, T must be between negative 41 degrees, 41.8, and positive 41.8. And then T must also be between 138.8 and 221.8 degrees. That's where I get my domain restrictions from this. Do y'all follow all the little subtleties of this, though? You have to convert a linear, a nonlinear, this is a trigonometric nonlinear inequality into a equality. Find your solutions. Realize that the inverse trig function left out 2 of your solutions. Get all of them. And then from there, test your regions and confirm your domain. All right, it's a good time for a break. I've got to run down to my office to grab your take-home tests. So let's say we'll be back at, what do you say, 3? Take an extra long break, 15 minutes. 3 o'clock, we'll be back. Okay, we can utilize computers to graph examples for us. So this is a toroidal spiral. Y'all know what a torus is? Torus is basically like a donut, and this is a spiral that goes around the outside of a torus. Doesn't look like it's moving. There we go. Speed that thing up a little bit, right? So it's drawing a spiral around a torus. This is called a trefoil knot. And it's kind of hard to see it, but this curve draws a knot. You see that? It draws a knot, goes back through itself. The actual vector functions to draw these are in the book, but since I've got this open, I'll just reference it in here. Where is it? Here's the vector function for the toroidal spiral. So the first component function is 4 plus sine 20t times cosine t. The second component is 4 plus sine t, in parentheses here, quantity, this quantity right here, times sine t, and then cosine 20t. So if you were to try and graph that, plug in values of t, you would draw that toroidal spiral. The other one, the trefoil one, is, I think it's a pretty crazy one. Let me see. It's this right here. It's in your book. I just want you to see. It's not something you would naturally just look at and be like, oh yeah, that's going to draw this trefoil knot, you know. So that's why computers are useful, because they can draw these things for us. All right, now, differentiability, derivatives of vector functions. Okay, given a vector function in 2 or 3-dimensional space, the derivative of the vector function is, thank goodness for us, just the derivative of the component functions. That's all it is. The important thing is, if you take the derivative of a vector function, you get a new vector function. All right, so the derivative is, the answer is just a vector function. The geometric meaning of the derivative. In Cal 1, the geometric meaning of the derivative was what? The slope of the tangent line, right? Basically, if you take a function and you take its derivative, it creates a new function, and that function tells you the slope of the tangent line at every point on that original function. Well, it's kind of the same thing here. The thing you have to remember, though, is that if the derivative of a vector function is a vector function, it draws a vector, doesn't it? It draws a vector. The derivative is a vector function, so it draws a vector. How is that vector related to the original curve? Well, it's tangent to the curve. So our picture, I'll show you the picture first. Okay, so here we go. What we have is the blue is the original vector curve, r of t, right? R of t is drawn by these black vectors, and then the derivative vector function, right? The derivative vector function draws the red curves, or the red vectors. Now, these red vectors should be centered at the origin, but I've translated them out here so that you can see that those vectors, if you move them, they're always tangent to the curve. Okay? So it follows tangent. Now notice also that the length of that vector is changing also, isn't it? Looks like as I was going on, it's getting longer, right? What do you already notice about this that's different from Cal 1? Is the blue curve a function in Cal 1? Would you consider that blue curve a function in Cal 1? No, because it would fail the vertical line test, wouldn't it? But when you draw curves with vector functions, it's okay to turn back upon yourself. Remember, the vertical line test was something that we used when we said, I'll stop it right here. Look, the vertical line test would be in the case where, let's say I try and plug in x is 1, right? X is 1 would be trying to spit out that value and the one down here, right? So you'd have one input, 2 outputs, which means it's not a function. Why is this a function? Well, because our time is what's being plugged in, right? And for every point in time, there is a vector. The vector up here, right, at that point in time, is completely different than the vector down here, even though in the sense of vertical line test, it fails, right? Do you all understand that distinction? It's because x is not our independent variable. T is our independent variable. Okay? So what we're able to do here is kind of find like a tangent line, but it's not the slope that we're getting, it's the actual vector that's tangent. So it looks like as we moved along, the vector got longer, right, as we moved, and it changed direction. So let's go back here and do this example. Find the derivative of t sine t, t cosine t. find the vector that is tangent to t sine t cosine t at t equals pi over 2, and then find the vector equation of the line that is tangent to that function at the curve, or at that point, pi over 2. So I give you R of t is t, is it sine? Sine t? And then t cosine t? Whoa. Okay, the derivative is just the derivative of each component. So what do I have to do here? Take derivative t sine t. Little product rule there, right? Okay, so we get sine t plus t cosine t. And then the other one, product rule again, cosine t minus t sine t. That is our derivative. I forgot to put the derivative mark there. There's our derivative. And we are asked now to find the vector that is tangent to the original curve at t equals pi over 2. So at t equals pi over 2, what we're really asking for is the derivative at that point, right? And so we plug pi over 2 into the derivative. What's sine of pi over 2? 1, and then plus, what's cosine of pi over 2? 0, so that's all gone. Okay, cosine of pi over 2 is 0, minus pi over 2 times sine of pi over 2. Sine of pi over 2 is 1, so we should just get negative pi over 2 here. So at t is pi over 2, the vector that is tangent to our curve is that vector, 1, negative pi over 2, right? Now we want to know what the vector equation of the line is that's tangent to our curve at that point. So geometrically, what we've done is we've gone to, let's see, pi over 2, right? See if I can go back to my initial settings here. Pi over 2. That's where I am right there. So at pi over 2, I've found this vector, the red one, and it is the vector 1, negative pi over 2. That's it right there, right? But now what we need to do is find the equation of the line that's tangent. So we want that line, the entire line, right? So what do we already have? What is that red vector really now going to be for us? The direction vector of our line, right? And the only other thing we need is what? A point. But don't we have that point right there? Or can't we get that point right there? That's a point on the blue curve. It's the point at the exact time pi over 2. Into the original one, that'll give us our R naught. And then that R prime of t is our V. And then we have the line. See the difference between, I mean, that's, the analogy is in Cal 1, we had a curve. We found the derivative, right, at a point, right? We found the derivative, and that gave us the slope. Then to find the equation of that line, we used y minus y1 equals m times x minus x1, right? Because we knew a point, the point on the line would be this point right here, x1, y1. What we're doing now is we're not getting an m, we're getting a v, a direction of our line, and then the x1, y1 is like our r naught. So we just put them together. See the similarity but difference there? Okay, so I just want r of pi over 2. What's r of pi over 2? So we're plugging in up here. Pi over 2 is 0. Okay, that's my r naught. This is my v. This is v. This is my r naught. And now we can come up with the vector equation of the line, right? Now I shouldn't call it r because r has already been defined in this problem, so we can call it something else. How about s? S of t, and it will be pi over 2 plus t, and then minus pi over 2 t. Is everyone comfortable with what I did there? Use R naught in here. That's my point, pi over 2 and then 0, and then this is my direction vector, so these get the t on them. 1t, negative pi over 2t. That's it. T is a real number. I don't really state that all the time. If you don't state t is a real number, then it's assumed that t is a real number. If you restrict the domain, then, you know, if you want to restrict domain, you need to explicitly say that. If not, we'll just assume t can be anything. All right, back to more notes here. All right, since that red vector, as we moved along the curve, that red vector was changing, right? It was changing direction and length. It makes perfect sense to define what's called the unit tangent vector, which would be a vector that still points in the same direction as our tangent vector, but we scale it so it always has length 1. And do you remember to make a unit vector, you take a vector and you divide it by its own length? That's how you create a unit vector. So if we take the derivative, which is a vector, and we divide it by its own length, then we create what's called the capital T, the unit tangent vector. So if I look at the same exact function, you see it's a purple vector there, T. Notice that T is always going to point in the same direction as the red one, but it's always going to maintain unit length. Okay, and sometimes that comes up, and it's useful to look at the tangent, the unit tangent vector instead of the tangent vector itself. So we just need to know how to calculate it. So what is this? What is the unit tangent vector for that same vector function we just had at pi over 2? I think what I'll do is I'll just add it to the bottom of this. What's capital T pi over 2? Well, this would be r prime of pi over 2 over the length of r prime of pi over 2. What did we say the derivative of pi over 2 was? What was it? 1 negative pi over 2. So 1 negative pi over 2. And then divide that by its length, which would be the square root of 1 plus pi squared over 4. And then you could scale each component by that. So 1 over square root of 1 plus pi squared over 4. And then the other one would be negative pi over 2 square root of 1 plus pi squared over 4. That all right? That's a vector that's going to point in the same direction as the tangent vector, but it's going to be length 1. All right, can I move on? I don't know if I want to go through this whole example, but let me point out what's important here. Well, you know what? I think the derivative would go fast enough that I could just do this one. But notice the difference between this problem and the one before. In the previous problem, I said, hey, here's a vector function, right? I said, find the equation of the tangent line at a certain point in time, right? Here, do I give you the point in time? I don't tell you what t is, do I? Not directly, do I? But can you tell me what t is here? What's that? Pi over 2. Well, what the hell? Pi over 2. Now, how can you tell? Well, whatever t you plug in, here, here, and here, needs to give you 0, 1, 0. Right? And it's almost too obvious. T, right, has to be pi over 2. And you can check it. Sine of pi over 2 is 1, and then cosine of pi over 2 is 0, sec is 0. So with this problem, you're going to try and find what? The derivative at pi over 2, right? That will give you your v, your direction vector. And then what about r naught? What vector can you use for r naught? This point right here, right? That point lives on the original curve. So just convert that to a vector. That's your r naught. Make sense? So I won't work it, but I want you to realize that either t is given to you or you have to recover t. One of the two things. That's just what that one draws. Now, the second derivative, just like we had the concept of second derivative in Cal 1, we have second derivative in this one. So it's just the derivative of the derivative. Now, smooth functions. This is a definition. A vector function r of t given on some interval I is called smooth if it's continuous. That means it exists, the derivative, exists on an interval, and as long as the derivative is not 0, except possibly at endpoints. This is weird, because in Cal 1, what did it mean? What did it mean in Cal 1 for a derivative to be 0? What did it usually mean? Where's the derivative 0 here? Where we had like max and mins, right? Right? Something like, you could also have something like this, though, right? Where it's not a max or min, like that. You'd have derivative 0 there. So in Cal 1, if the derivative was 0 in Cal 1, it was still okay as far as us calling it a smooth curve, right? It was nice and smooth, right? In Cal 1. But with vector functions, if your derivative is 0, something weird is happening there, as we're about to see. So we won't be able to call it smooth. So the question here is this vector function smooth for every t you could possibly ever plug in? Is it smooth? So r of t was cosine squared t, t to the fourth. All right, so let's find its derivative. The derivative of this is what? So a little chain rule on the cosine squared t, right? Taking derivative. What does it come out to be? Negative 2 sine t cosine t, which you could even use a half angle identity there, couldn't you? Or double angle identity. 2 sine t cosine t is actually sine 2t, right? But we just leave it like that also. Then derivative of the other one, 4t cubed. The question becomes, if it, is it smooth everywhere? Can that vector ever be 0? Yes or no? So, does there exist a t that makes that 0? Equals 0. Yeah. Now, how you could do that is just simply look at one of the components, right? To be able to get the 0 vector, that's a vector, by the way. To be able to get the 0 vector, did I put that in the notes? Is it 0 vector? No, it doesn't say it enough. This needs to be 0 vector. To be the 0 vector, then this component has to be 0, doesn't it? And the only way this component can be 0 is what? If t is 0. And now we just check. T being 0 here, does that give us 0? Yes. So at t equals 0, we get that the derivative is actually the 0 vector. So is it smooth everywhere? No, right? It's not smooth everywhere. Now let's take a look at what this graph is, all right? Here's the graph. And that's what's happening at t is 0. So let me play this. Let me make it a little smaller here. Slow it down just a bit. All right, so keep an eye. T is negative. Here comes my tangent, right? T is 0. Now it goes this way. You all see that? So t negative coming up. And then at 0, what happens there? Look what happens to that derivative, the vector. Okay? All of a sudden, it's like this, and then in an instant, what happens? Changes direction. So your derivative is not moving smoothly, right? That tangent line goes and all of a sudden pops the other direction. Now, it got shorter as we were getting there, but it changed direction instantly. The analogy in Cal 1 would have been where we were told derivatives don't exist in functions in Cal 1 at cusps, right? Or if you had like an absolute value function or something like that. Remember, we were told at corners and cusps, derivatives didn't exist. And that was because what happened, again, was very similar to what just happened. We have tangent lines that are positive, right? Positive slopes, and all of a sudden, we get on the other side of that cusp, and everything's flipped to negative tangent, negative slopes. So a derivative cannot go from positive to negative in an instant. It can go over a hump smoothly, right? Positive slope slowly getting flatter and flatter, then it goes over and becomes negative. That's okay. It's just that the corners can't happen. So that's what's happening for us with the vector function, except that in order to determine where this thing happens, the first derivative is 0, and that's what's going to occur. Okay? What is this? I must have just accidentally left that in from the previous code. All right, some properties for derivatives of vector functions. Again, we had this in Cal 1, right? Derivatives properties. So if I have the derivative of the sum or difference of two vector functions, you can just split it up and do derivative one at a time. That's great. If we have a constant, we can pull that constant out, then take the derivative. All right, this is important because there's something subtle here. F of t here is what type of function? A scalar function, like x squared, or sorry, not x squared, t squared, right? And then u of t is a vector function, so it could be a vector with 2 components or 3 components. And so it's saying if you have a scalar function in front of a vector function, and you want to take the derivative, you can do, what does that look like to you? It looks like the product rule. That's exactly what it is. It's the derivative of the first function here times the second, which is a vector function, plus the derivative of the vector function times the scalar function. All right? So that extends. Now, look at this one. What if you want to take the derivative of 2 vector functions that are being dotted? What does that look like to you? Product rule again, except instead of this being multiplication, that's what? Dot product. And now if you have the derivative of a cross product of 2 vector functions, again, it's product rule with cross products this time. And then finally, if you have a vector function where you're evaluating it at f of t. Now what the heck is that? Usually this is just u of t, right? But what if this in here, this t is not just a t, it's a function of t, and you want to take the derivative? It's chain rule. That's it. It's the derivative vector function evaluated at f of t times the derivative of f of t. So that's your chain rule right there. So those are properties you should just keep in mind. All right. Show that if r of t equals cosine t sine t. What's cosine t sine t? Circle. And this is a 2-dimensional vector function, right? Then that show that if that's your vector function, then r of t is orthogonal to r prime of t for all t. That r of t is a vector, right? want to show that it's orthogonal to r prime of t for every t. So our original vector function was cosine t sine t, and the derivative of that was negative sine t cosine t, right? I want to show that the function is orthogonal to its derivative all the time. So how do you show orthogonality? Dot product, right? I want to show that r of t dotted with r prime of t is 0, right? That's what I want to show. What's r dot r prime? So you do these two, right? And you multiply those and you add those two multiplied. So isn't that just 0, right? That's just negative sine t cosine t plus cosine t sine t. That's 0. Do I need to write that out, or is that clear? Okay. What did we say it drew? R of t drew a what? Circle? Does it make sense that anytime you take the derivative anywhere on this thing, the vector is going to be like this, right? Tangent. And then what was the vector that drew the circle? It came out from the origin, right? And we're saying that these two vectors are orthogonal. Not a very good picture, but do you see? The derivative is orthogonal to the vector function, always. Now, this next example is really neat. Oh, here I was. This is what I was trying to draw, right? Sometimes I forget what I have in here. All right. Look at this one. This is a great problem. This is one of those problems that you could probably work on for a long, long time and not get it. I mean, it's just, there's nothing straightforward about it. Show that if the magnitude of a vector function is constant, then r of t is orthogonal to r prime of t for all t. Think about that for a second. If the magnitude of the vector function is constant, so as t goes by, you're drawing vectors, right? But all the lengths of those vectors have to be what? Constant, which means they have to be the same, right? If your vector function does that, so let's say my arm is C, and I start drawing vectors, and let's say I'm in three-dimensional space, right? As long as the vector lives on the tip of my hand, right? And I'm drawing these, and it doesn't matter what's happening down here, up here. How can I show that the tangent vector is always orthogonal to this vector? Y'all see that that's what we're trying to show? See, in the previous problem, we were able to take r and then take its derivative and then dot them, right? But here we don't have anything to dot. We don't have r of t, do we? We have its magnitude, but we don't have the actual vector function. So, any ideas or? No, that's the thing. This is arbitrary. This is arbitrary. Okay, so we had a property a while back. Let's see if you remember this property. Do you remember, pardon? But we're saying the magnitude of the function is constant. That doesn't mean the function itself is constant. Do you agree with this? Now, if you look way back in your notes when we first introduced dot product, I gave you some properties of dot products. This would have been, man, where are those notes? I want to point you to the notes so that way you know it's somewhere in here. Properties of dot products. 10.3.2, thank you. 10.3.2 says that if you dotted u with u, that it turned out to be the length of u squared, right? So do you agree that if I dot r of t with r of t, it's the length of r of t squared? Yes? We okay with that? But what's the length of r of t? In this problem, what did they tell us the length of r of t is? C? So this is c squared? Yes? We follow that? Okay. Now, I haven't shown anything, right? What am I trying to show? I want to show that when I take r of t and dot it with what? The derivative, that it should come out to be 0, shouldn't it? Yeah? Okay, so watch this. I'm going to take the line above, rt dot r of t equals c squared. And it's an equation, right? Do you all agree this is true? I mean, from what we have up here, this is true? For this given r, that should be true. Now I'm going to differentiate both sides of the equation with respect to t. So I'm going to take the derivative on the left side with respect to t of r of t dot r of t. And then what's the derivative of a constant on the right side? Yeah, that'll be 0, right? So the right side of my equation is 0. And the left side, I can use the properties that I just talked about, right? What's the derivative of a dot product? Right here. The derivative of a dot product would be the derivative of the first one, right? Dotted with the second plus derivative of the second dotted with the first, right? But they're the same function, aren't they? So shouldn't this be the derivative of r dotted with r of t plus the derivative of r again dotted with r of t equals 0? Do you all see it? This is the same as this, isn't it? So two of those, 2r prime t dotted with r of t equals 0. Divide both sides by 2. R prime t dotted with r of t equals 0, which is what I wanted to show, right? QED, little box at the end, that's what I wanted to show. That means we're done. I've proven what I wanted to. Are you convinced, though? I mean, what makes something like this, a proof like this, a little challenging is the fact that, like, how would you know to just write r dot r and then differentiate, right? The only thing that would let you know that is that what you wanted has r with its derivative, and maybe you kind of see that if in a product rule you would get that. But other than that, I mean, it's not obvious. All right, so we've got that. Okay, some applications of derivatives of vector functions. So some of the things we can do with derivatives. So I start this off by having you look at two completely different vector functions, r1 and r2. I have you look at them for all t values greater than or equal to 0. So one of them is t squared, the other one is t squared t to the 4th. Do you agree that r1 of 1 and r2 of 1 are the same value? So if I plug in 1 here, I plug in 1 here, I get the same thing. Yes? If I plug in 4 into the first one, and I plug 2 into the second one, do I get the same vector? Yes? In fact, what we can see is if you start plugging in different values of t, this is R1, it'll draw the exact same curve as R2. They draw the exact same curve. The difference between the two is how quickly they draw them. So can you all see the points there? Time is moving right now. Look how fast R2 draws the curve versus how fast R1's drawn. Now if I throw in their derivatives, remember the derivative is R prime, is the vector that's tangent. If I throw those into the picture, take a look at the difference between them. What's the difference between those vectors? Look at how big the vector is over here, right? How long it is. That length is somehow representative of how fast that point is moving as time changes. So even though they draw the exact same curve, the derivative vector function somehow connects how fast it's being drawn. Do y'all see the relative difference? Now if I compare them, if you can put some values in there to kind of compare the difference, right? Like if I take the derivative of this vector function here, I take its magnitude, I get 8.6. If I go to the exact same point over here, where I draw that same point, take its derivative and take its magnitude, it's 32.2. It's almost 4 times, right, bigger as far as the length of this vector to this vector, which represents that point's moving a lot faster. And if you compare them side by side, well, that doesn't work real well. Okay. So what that leads us to is this. If R of t is a vector function representing the path of a particle or object through space, 2- or 3-dimensional space, then we call it a position function. V of t, the velocity function, is just the first derivative. This is all very similar to what we've had before, right? You should have in Cal 1, Cal 2 talked about this. And then if the v of t, which is the derivative, is a velocity function, vector function in fact, then the speed of the particle is the magnitude of that vector. The magnitude, the length. And now if we take the derivative again, the second derivative, it's called the acceleration function, and that again would be a vector function. The larger the magnitude of the derivative, the faster the particle is moving at that point in time. Let's see. A couple of examples here that I might consider. Sorry, I'm looking for a specific problem. There we go. Okay. They were a little hidden there. So let's say I tell you this. If r prime of t is the vector function t e to the t, t e to the t. And I tell you that r of 0 is the vector 1, 1, 1. I would like for us to find r of t. So what have I given us? I've given us the derivative vector function, right? I've also given us an actual vector at a particular point in time for the curve r, right? R of 0 is 1, 1, 1. And from this, I want to somehow rectify what r of t is. So I've given us the velocity function. We need to go backwards and recover the position function. Did you ever do that in like Cal 2? Start with the maybe acceleration function, go backwards to velocity, then go backwards to position. Same exact thing, except we're having to go backwards from a vector function to another vector function. So how do you think we're going to get there? Right? V of t equals r prime of t, right? So how do we get to r? How do we go backwards? Integrate, right? We're going to integrate. So if we integrate this, right, take the antiderivative of the derivative, we should be able to go back to recovering now with respect to t, right? We should be able to go back and get r of t. Can you integrate that? How do we integrate? We integrate each component. Now, on your notes, let me point to something because kind of I think I jumped over something, didn't I? Let me see, did I double tap that? Do you have anything after this? Oh, okay, that's what happened. Okay, integration. All right, well, let's do what I'm doing right now, but just keep in mind that I'm going to be using note 10.7.17. If we have a vector function, we can integrate it by integrating term by term. All right. So let's go backwards. So that's what we're going to do. R of t should be equal to the integral of r prime of t dt, which should be equal to the integral of each of these. T dt, integral e to the t dt, integral t e to the t dt. Integrating each component, antiderivative of t is 1/2 t squared, right? Antiderivative of e to the t is e to the t. And then what's the antiderivative of t e to the t? How would you do that one? Wolfram alpha? Right? No. Integration by parts? Right? Integration by parts? Y'all remember how to do that, right? You'll need it on your test or on your take-home test. People learn it different ways, right? Depending on, your instructor. Some people do these little boxes like this. How many of you learned some variation of this? Yeah? All right, du and then 1 dt. How many of you learned ultraviolet minus voodoo? A lot more than I thought. Okay. So this would be ultraviolet minus voodoo in this case. So it would be t e to the t minus e to the t. Now, what do we always get when we integrate something? When we do a just general antiderivative, not a definite integral. If we do indefinite integrals, what do we always have? Constant, right? Constant of integration. But when you're integrating vector functions, your constant is not a constant, it's a vector constant. In other words, it's a vector that is that has constant components. So what I'm going to put out here is some constant. I could either write it like this, a constant, but I need to everyone to know it's a vector, or I could write it as a vector, and just each component, I don't know what it is, C1, C2, C3. Do y'all see what I'm saying? Either way, I prefer this way because we actually need to figure out what these are, right? Any questions on this, though? All right, so far what I know is that the R function I'm looking for is at least that plus something that I don't know. How are we going to get the part that we don't know? What piece of information have we not used? The initial, what we call initial conditions. The initial condition that R of 0 has to give you 1, 1, 1, right? I need that now. So come down into this, which is this, and plug 0 in and tell me what you would get. So R of 0 into these pieces here, you would get what? 0, 1, -1, plus our constant 1, constant 2, constant 3. That has to be equal to what? According to my initial condition, that has to be equal to 1, 1, 1, right? What can you do here to solve for these constants? Subtract this vector from both sides. Subtract the vector. So leave the C1, C2, C3 there, and then equals, take the vector on the right, 1, 1, 1, subtract the 0, 1, 1, -1, and that gives you what? 1, 0, 2, subtracting a negative. So now you know what your constant is, don't you? Now go back up and rewrite R with that constant, and go ahead and add the two together. So put that and that together. So what would we have? I'll try and leave R there. R of t is the 1/2 t squared, right? Plus 1. Then e to the t plus nothing, so I'll just leave it. And then t e to the t minus e to the t plus 2. And that's it. Sign-in sheet. Okay, what about this one? I'm not going to work through this, but let's say you have a function R of t is this, and you're asked to find the integral from 1 to e of R of t dt. You would integrate this term by term, wouldn't you? Or component by component. What's the antiderivative of e to the t? E to the t. This one? How would you integrate that? U sub, what would your u be? T minus 1? That'd work out pretty good for you. How about natural log t? Depending on your instructor, you may have memorized that, or you do integration by parts, yeah. So either way. That's the other way, careful. It's t natural log t minus t. Yeah. So, you work through it. Once you do that, you plug in your two limits of integration. Should we just do it, or no? How about this one? I give you R prime, I give you initial condition, right? Hey, that's the one we just did, isn't it? Hey, all right, cool. I knew I had it somewhere in there. So we just did that one. This is what we were talking about. If you have velocity, you can get velocity by integrating the acceleration function. You can get the position by integrating velocity. All right, so look at this one. I give you that A of t is t e to the t e to the negative t, and then I give you two initial conditions, right? From that, I ask you to go how far back? All the way to R of t? So what would the first thing you'd need to do here? Get the velocity. How would you get velocity? Integrate this, right? When you integrate that, aren't you going to get a constant? C1, C2, C3? Are you going to be able to figure out what C1, C2, C3 are? Using what? The initial velocity condition. So V of 0 is going to give you this. Then you get C1, C2, C3. Then you rewrite it. Now you'll have V. Once you have V, what? Integrate again, and you'll come back and you'll get R. And that R will have a constant, which you can call C1, C2, C3 again, or you can just call it D1, D2, D3, change it, whatever. It doesn't matter. Then you use the initial conditions again, and that'll give you your position. This is not the homework assignment. I will have to send you something. All right, how's everyone feeling? Tired? I know I'm kind of running out of gas up here myself. What is left here in this section? Arc length. 1, 2, 3, 4, 5, 6, 7 notes. You think y'all can handle 7 more notes in a little bit of time? Y'all want to stand up and stretch out, or just get it over with? Okay. All right. Here we go. Last section. So we will have finished the entire chapter 10 in 3 days. Wow. That's the plan. Yeah. That's the plan. Yeah. It's a lot of work to bound those things. Yeah. Anybody who wants to maybe earn extra credit can always come help me. Money. No, they have all the material I need to do it, the machine and everything, but it's tedious. Yeah. Okay, arc length and curvature. Have I handed the exams out? Okay, let me hand those out. So there should be some there. Should be enough. I think there's more than 4 there. Okay. Just 5 problems. Everything here on this mini exam is pretty much through 10.5. Well, I take that back. I forgot about the other side. Yeah, just forget. It's all out of chapter 10. First one, find the equation of the plane. So you're thinking already, what do I need for the equation of a plane? A point. And another point. And what do you need for the equation of a plane? If I want to define a plane, what do I need? What kind of direction? Normal vector and a point. That's it. That's all you need to define a plane. Normal vector and a point. So, but I need to find the equation of the plane containing the point of intersection of two lines. So two lines cross each other, they intersect. That point needs to live on your plane. Well, there's the point I'm talking about you need. But it's also parallel to another plane. So the plane you're trying to find is parallel to some other plane? I don't know. That's what you're going to have to determine. But, I mean, again, I'm just trying to get you to start thinking about, as soon as you read it, what do you need? And then just go from there. Okay? Next one, find the equation of a line. Okay, what do we need to define the vector equation of a line? A point and direction vector, or 2 points and you can create your direction vector. Okay? But the thing is, I throw in all this other crap. Find the equation of the line through a point. Hey, I gave you the point already, didn't I? But the line you're looking for has to be both parallel to some plane and perpendicular to some other line. You have to think about what that means. Okay, moving on. Number 3. This is kind of what we talked about earlier today. Find the shortest distance between the center of a quadratic surface. Quadratic surface, all those things we looked at earlier today. Find the center of it. So that may not be a sphere. But remember we had centers of these things? Like the one we did in class, I completed the square and did all that, and then we talked about where the center was. Shortest distance between that center and the line of intersection of two planes. Number 4, given the vector function r of t equals blah, all of that, find the limit as t goes to infinity. So I promised you L'Hopital. You get it right there. Be real careful with that, because if you take a limit on one of those, like it would be like if you ever get like 0 over 0 and you say undefined or something like that, like you'll get no credit for that problem. Every one of those component functions has a limit at infinity, all right? Every one of them. So you just know there is an answer to this, okay? This does approach a vector. You just have to figure out what each one is. So, and then the last one, find the vector function, so r of t, which represents the intersection of a cylinder and a plane. So remember I did that one with the blue curves, the intersection of the two cylinders? Something like that here. Now, use the vector function you just found to determine the equation of the line which is tangent to that curve you found at a specific point. Got it? So number 5, a cylinder runs into a plane, right? Creates a curve. That curve, I want you to find the equation of the tangent line to that curve at a specific point on that curve. Now, don't just think of it as a cylinder in a plane like this and your answer is a circle, because it may be twisted or tilted, right? So that equation might be something else. Mess with it. So this is due beginning of class next Monday. All right, now I have 30 minutes. I'll see how I can get through this. See how you get through this. Arc length and curvature. Suppose r of t is a vector function in two-dimensional space. All right? And that t varies from a to b. So this is a change. We're actually looking at a vector function on some interval of time between a and b. And we're also assuming that the path does not traverse itself more than one time. Like if I draw a circle, I can keep drawing the same circle over and over and over, right? But if I restrict it, then I can just make it draw half a circle or maybe one full circle by restricting the time. If we restrict our time and make sure we do not draw over ourselves more than once, then we can define the arc length, right? how long that circle is, or how long that curve is. And it's given to us by this formula. So the length of the arc is the integral from A to B of the magnitude of the derivative. And the magnitude of the derivative is this, right here. Square root of the derivative first component squared plus the derivative second component squared. Now we can look at this as an infinite sum of infinitesimally small tangent vectors. So all you're basically doing is taking some curve, and this works in three-dimensional space, as we'll see also, and we're taking this tangent curve and we're cutting it into smaller pieces, and we're adding up the lengths of these things. So the smaller the piece is, the smaller increment of time, the closer that tangent, the length of that tangent becomes to the actual arc length. So hopefully you've seen a lot in Cal 2. We cut things up for like very small pieces to get an approximation, then let them go to infinity. Same thing here. I think the next note, no. Next note would be 3D. No, that's a picture. There, 3D. Okay. So let's do this one real quick. What's the arc length of cosine t sine t on 0, 2 pi? What is that? I mean, just tell me without doing any calculation here. What does r of t draw on the interval 0, 2 pi? Unit circle, right? What's the arc length? That would be the circumference, wouldn't it? What's circumference of circle radius 1? 2 pi r is 1. So 2 pi? We should get 2 pi. Okay, r of t cosine t sine t. R prime of t. So I'm looking for its derivative, which is negative sine t cosine t. What's the magnitude of that? Square root of, when you square negative sine t, you get sine squared t. Plus, when you square cosine t, you get cosine squared t. Pythagorean identity, that's 1. That's just 1, right? Now, according to this, the length of the arc will be the integral from 0 to 2 pi. I'm using 0 to 2 pi because that was, t was going from 0 to 2 pi, right? And then what am I integrating? Magnitude of r prime, right? That's just 1 with respect to t. That's just t evaluated from 0 to 2 pi, and that gives you 2 pi. That just verifies what we already knew, right? So if you want the arc length of a curve, you just need to be able to differentiate it, find its length, and pray that you can integrate whatever that is. We got real lucky here, right? Because it came out to be 1. But as you might imagine, if it's not 1, you're going to have square roots involved, and it could be a really nasty integral. Okay, everything that we just did extends into three-dimensional space. Your curve's still going to be restricted between A and B. We still can't go over ourselves, can't draw on top of ourselves again. You can cross through, but you cannot overlap. Like a segment of the arc of the curve cannot draw right on top of another segment. So that's what they mean by traversed only exactly once. And the only difference is it's still a magnitude of derivative, but we have that third component in there. Okay, so let's look at that one. R of t cosine t sine t t. Cosine t sine t. What does this one draw? What does that one draw? It's trying to draw circles, but the z-coordinate, which is t, keeps getting bigger, so that was that kind of spiral thing. It was more like a spring, right? Fixed radius. Now, what were the points I said this went from? Notice I did not give us a restriction on time, did I? 100, negative 10 pi. Okay, we'll deal with the point in a second. Let's get the derivative, and let's find its magnitude and see if we're going to be able to do anything about this. Derivative of this, negative sine t, cosine t, 1. The magnitude of that is square root of, oh yeah, it's going to work out nice. Sine squared t plus cosine squared t plus 1. But that's just square root of 2, isn't it? It's not going to work out that nice on your take-home exam, right? You're not going to have this on your take-home exam. Next one you will. But I wouldn't expect that it would work out that nice. There will be at some point some opportunity for you to show and demonstrate your Cal 2 expertise in integration. So you can show off a little bit at some point. What now? The length is integral from, you see, this is where we're going to run into a little bit of an issue because I didn't give us the interval. But we know that at t equals something, we were here, right, at the first point, and then t equals something, we're at the other point. So can you tell me, from looking at this right here, what the t is? 0, right? 0, because that's my third piece here. Whoa. 0, plug 0 in here, here, and here, and that does give you this point. So t equals 0 is probably where I'm going to start. And then what about the other one? Pi, if you plug pi into r, you get the other point. So again, the interval 0 to pi is kind of hidden in the point. You just have to kind of extrapolate it out of there. And now I'm just integrating root 2, right? With respect to time, or t. It's just root 2t, 0 to pi. So you get pi root 2. Yeesh. Questions? We're getting close. Man. I think I'll stop at curvature. Did we just do that one? Yeah. This will be our last example. We're not going to quite finish. I want to save curvature for next time. I need you all to be a little fresh for that. All right, 2t to the 3 halves cosine 2t, 2, 3 to the t. All right, we're asked here to find the arc length of this curve on t between 0 and 1, right? Okay. So find the derivative, which would be three root t, good. There you go. Okay. That's our derivative. Magnitude. Square root of 3 root 2, but square it, so 9t, right? And then plus 4 sine squared 2t plus 4 cosine squared 2t. All right, can you clean that up at all? What can you factor out here? Out of just those two? Can you pull just a 4 out of those two? You make this a 4 sine squared 2t plus cosine squared 2t. Can I do that? And then what's sine squared 2t plus cosine squared 2t? 1. So this just turns out to be square root 9t plus 4. Questions? We want to integrate that to get the arc length. We want to integrate that from 0 to 1 because it was given to me, thank goodness. Square root 9t plus 4 dt. And that would just be a straight, clean substitution. Not a lot really going on there. Okay? We'll save curvature. Yeah? All right, is there anything else? The sign-in sheet went around. Anybody need that? Okay. Okay. Where are you? Okay. Okay. Well, if it turns out to be an issue, we'll fix it. Yeah.